Welcome to the module Event-Based Simulation. Motion studies can be time-based or event-based. In time-based motion studies, parameters such as motors are triggered with time. In event-based motion studies, parameters are triggered by events. In this module, you will learn how to set up an event-based motion study. In this module, you will learn how to create sensors to trigger or stop events, create a set of tasks triggered by sensors, apply servo motors, and create events with specific timing and logic. This module is divided into several topics. Click the topic titles in the list for a brief overview of each topic. The sorting device shown on screen is used to sort two types of boxes, yellow with holes and solid red. In this simulation, the boxes will be sorted by type into the bins as shown on screen. The vertical motion of the boxes is caused by gravity. Once the blocks fall, a sensor will monitor the front of the block to determine if it has a hole or if it is solid. Logic will be programmed into the analysis so that the boxes will be moved to the correct bins through a sequence of servo motors. A servo motor is a rotary actuator or linear actuator that allows for precise control of angular or linear position, velocity, and acceleration. It consists of a suitable motor coupled to a sensor for position feedback. You can use servo motors to implement control actions for event-based motion analysis. You can create the following types of linear or rotary servo motors in SolidWorks Motion: displacement, velocity, acceleration. When triggered, servo motors control the motion of a component. Let's see how to apply servo motors. Click Show Me to launch a demonstration video. The assembly, sorting device, has been opened from the Case Studies folder. To save time, the motion study has been renamed as Sorting Device. Ensure that the type of study is set to Motion Analysis. Verify that the document units are set to millimeters, grams, seconds. Now, let's define the linear servo motor for actuator 1. Click Motor and select Linear Motor. For motor location and motor direction fields, select the flat face of actuator 1, zoom out and scroll down. Click the Motion Type drop-down and click Servo Motor. Click the Motor Type drop-down and select Displacement. The parameters of the servo motor, such as distance extended and speed of extension, will be controlled within the Event-Based Motion User Interface, which we will explore shortly. Click OK. Rename the motor to Actuator 1. To do so, slowly double-click Linear Motor 1 and type Actuator 1. Now, follow the same steps to define two more linear, displacement-based servo motors. We have defined two more linear, displacement-based servo motors and renamed them to Actuator 2 and Actuator 3, respectively. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about applying servo motors. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Sensors can be used to trigger or stop the motion in event-based simulations. 3 sensor types can be used in event-based simulations. The interference detection sensor, used to detect collisions. The proximity sensor, used to detect the motion of a body crossing a line. The dimension sensor, used to detect the relative position of a component from dimensions. Let's see how to add sensors and create solid body contacts. Click Show Me to launch a demonstration video. We will add 2 proximity sensors to control the system. Sensor 1 will be used to detect the solid boxes on the bottom platform of the holder. In the event-based motion study, Sensor 1 will trigger Actuator 1 and push the solid red block out a specified distance. Likewise, Sensor 2 will be used to track the hollow boxes. Click Sensor. Click the Sensor Type drop-down, and then click Proximity. For proximity sensor location, select the flat face of the sensor sorting device and then scroll down. Now, we will select the solid boxes. Note that you can select them in any order. However, for demonstration purposes, we will select the first solid box for the components to track field. Then, select the second solid box for the components to track field. Enter 12 mm for proximity sensor range. In summary, the sensor will be triggered when a solid block is within 12 mm of the top surface. Click OK. Expand Sensors and rename to Sensor 1. Similarly, define proximity sensor number 2 to track the boxes with the holes. To do so, click Sensor. Click the Sensor Type drop-down and click Proximity. For proximity sensor location, select the flat face of the right sensor sorting device and then scroll down. Now, we will select the boxes with the hole. Note that you can select them in any order. However, for demonstration purposes, we will select the first box with the hole for the components to track field. Then select the second box with the hole. Specify 12 mm for proximity sensor range and click OK. Rename the newly added sensor to Sensor 2. Now, let's define the solid body's contact between various components of the assembly. Click Contact. Ensure that Solid Bodies is selected as the contact type, and click Use Contact Groups. Turn the assembly around, and for Group 1, select all the boxes. Click Group 2, select the holder, and the cylinder of Actuator 1. Click Material. For Group 1, ensure Acrylic is selected. For Group 2, select Steel, Dry. Keep the rest of the settings as they are and click OK. Following the same process, we have created Solid Bodies contact for all the boxes. Similarly, create Solid Bodies contact for Actuator 2 with 2 solid boxes in Group 1 and the sorting bay and cylinder in Group 2, and then select Acrylic for Group 1 and Steel, Dry for Group 2. Similarly, create solid bodies contact for actuator 3 with 2 hollow boxes in group 1 and the sorting bay and cylinder in group 2, and then select acrylic for group 1 and steel dry for group 2. Now, let's apply gravity. Click Gravity. Define gravity in the negative y direction. Click OK. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about adding sensors and creating contacts. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. Event-based motion requires a set of tasks triggered by sensors. Each task can be sequential or can overlap in time. Tasks control and define motion of the components during the simulation. The motion is defined by a triggering event and its associated action. Each task is triggered with a triggering condition that depends on the status of a sensor or the start or end of some other task in the sequence. The following is a list of actions that can be specified in a task definition. Stop, to stop the motion of a component. Motors, to turn on or off any motor or change a constant speed of motor according to the selected profile. Forces, to apply or stop applying any force or change a constant force according to a selected profile. Mates, to toggle the suppression of a selected mate. Let's see how to set up an event-based motion study and define tasks. Click Show Me to launch a demonstration video. Now we will see how to define tasks. Switch to the event-based motion view. The first task for the system is to move the lowest solid box along the holder platform to the position where actuator 2 may push it into bay 1. This task will be triggered when the bottom solid box activates the proximity sensor 1. Because this sensor triggers an event when the solid box is 12 mm above the platform and to provide enough time for actuator 2 to fully retract, A 0.1 second time delay for this task will be specified. Click here to add a new task line. For name, enter Push SolidBox. Click the selection button in the trigger field to open the trigger dialog. Expand Sensors. Then select Sensor 1. Click OK to close the trigger dialog window. Back in the Event-Based Motion view, complete the Trigger section by setting Condition to Alert On. Note that, in this case, the condition field is set to Alert On by default. Enter 0.1 seconds in the Time Delay field. The task definition will complete with the specification of action. In this case, the action comprises of Actuator 1 motor pushing the solid box 75 mm along the platform. Click the Selection button in the Feature field, and then click Motors to expand it. Click Actuator 1, and click OK. Click in the Action field and select Change. Enter 75 mm in the Value field. Then enter 1 second in the Duration field. Click in the Profile field and select Harmonic. Let's define the second task to retract Actuator 1. This task should be triggered after task number 1. We will create this task with Retract Actuator 1 as the name, Push SolidBox as the trigger, Actuator 1 as the feature, Change as the action type, -75 mm as the value, 0.2 seconds as the duration, and Harmonic as the profile type. So far, we have pushed the solid red block out with Actuator 1, then retracted Actuator 1 to its original position. Now, we will push the red block into Bay 1 using Actuator 2. We will create a third task with Push SolidBox to Bay 1 as the name, Push SolidBox as the trigger, Actuator 2 as the feature, Change as the action type, 50 mm as the value, 0.6 seconds as the duration, and Harmonic as the profile type. Similar to the second task, in the fourth task, we need to retract Actuator 2 in 0.1 second. This task must be triggered by the completion of task Push SolidBox to Bay 1. Add a new task with Retract Actuator 2 as the name, Push SolidBox to Bay 1 as the trigger, Actuator 2 as the feature, Change as the action type, -50 mm as the value, 0.1 second as the duration, and Harmonic as the profile type. Up till now, we have created 4 tasks which include the action of pushing the solid box to Bay 1. Now, following the same process, we have created tasks for pushing the hollow box to Bay 2. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about setting up an event-based motion study and defining tasks. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Let's see how to solve the event-based motion study. Click Show Me to launch a demonstration video. Now that we have defined various tasks, we will set the simulation properties. This will allow the simulation to solve in a reasonable amount of time with adequate accuracy. Click Motion Study Properties. Set frames per second to 200 and scroll down. Then select Use Precise Contact and scroll down. Click Advanced Options. Since we want to speed up the simulation and we are not interested in force results, we will relax the maximum integrator step size value to 0.05 seconds. Click OK. Click OK again. Switch to the timeline view. To provide the new end time value, right-click Key Properties and click Edit Key Point Time. Set the key time to 7.5 seconds. Click OK. Switch back to Event-Based Motion view. Click Calculate. It takes approximately 15 minutes for the simulation to complete. Switch to the timeline view. Here, you can see the result of the event-based simulation. Each key indicates the beginning, end, or a change in the motion of the system components. It also indicates the duration of the whole cycle. The timeline view provides insight into the duration of the whole operation. Each task's start and end is identified with a time key. Click Save. And close the file. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about solving an event-based motion study. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. You've reached the end of the module Event-Based Simulation. Here are the key takeaways from the module. Click each tab to learn more. Here is a chance for you to practice what you have learned. Offline exercises are available for this module. To attempt these exercises, you must have access to a SolidWorks installation. To complete each exercise, download the self-extracting executable file from the eCourse details page on mysolidworks.com. This file contains the sample models and exercise PDF file for every module in the eCourse.